Morning. How are you? Good. So this is the tool that I was talking about previous time. You have a MATLAB tool where you can play with root locus without writing transfer functions or doing anything like that. You can point and click. Very convenient tool. So you have tool is called root locus, obviously, but it's RL2 command in MATLAB. So if you run that kind of command in MATLAB, this opens that GUI. RL2. Can you see it? RL2. Very interesting tool. So here you have all of these poles and zeros that you can actually plot or draw on the screen. So for example, you want to add poles here. So just clicking on that X here, and adding whatever poles you want. Right? You can add zeros. You can add complex poles wherever you want them to be. Okay. And then you can also move them wherever you want them. And then you can move also the gain on the plot, so you can actually see what kind of response you will get with different locations of the poles and zeros and so on. So you have all of these things are movable. So you can put multiple zeros, poles, draw whatever you want. You can delete them, zoom in, zoom out to have all of the other functions. You have design requirements. You have all kind of things. You can add all kind of requirements for your design. For example, settling time, overshoot. So let's say settling time is 1. So you need to be behind that line here. Okay, so this is your constraint on settling time. Right? So you can place that all of your poles in closed loop will be all to the left if you want to. Okay, so you can design the trapezoid or whatever shape it is that your system will be of particular functionality, okay, particular performance. So it's a very nice tool. You can play with also with these values. I think like peak response, you can get numbers here without writing any code. Like if you want, I don't know, settling time. So your settling time, 3.09 seconds. There, okay. And you can play with the location of this poles. You can do whatever you want, and this will give you a picture of root locus, so you'll clearly see how it's supposed to look like without knowing even transfer function. And this helps a little bit with design of root locus in general. Okay, this will give you also intuition, like you can play with the different locations of poles and zeros, trying to guess how it's supposed to look like, right? Without writing transfer functions. Okay, any questions on the previous lecture? Homeworks? Anything else? All right, so let's get back to our symmetrical root locus. So previous time we talked about symmetrical root locus, which is alternative to Riccati equation solution to find optimal controller, which is minimizing particular J function, which is cost function for optimal control. Now we know that we can deal with simpler kind of J functions, and this is kind of limiting in a sense, but you have symmetrical root locus for generic MIMO functions as well. For more inputs, more outputs, it becomes matrix equation instead of algebraic equation as we solve right now. And today we will just show some examples which are technically telling you how to do that using symmetrical root locus. So we will go through numerical examples. We'll solve a few examples. One easy example, which will be practically repeating one of the questions that we solved with Riccati equation, just to see that we get the same kind of thing. Another question will be kind of very tricky, in a sense. I mean, not too tricky, but kind of tricky. So we will try to design something optimal for a system for which you are not supposed to design anything optimal. System will not be really observable. Okay, so it will not be good system, nicely behaving system, right? So this will be example like what could happen if you try to do all kind of things that you're not supposed to do, right? It will be okay. I mean, we will design some controller will be fine. The thing is that you will not have unique solution as promised for all optimal controllers. So you have theorem, if you remember, of uniqueness of the solution of controller, which means you might have only one optimal controller which solves your problem. But in that case, you might have multiple different controllers which minimize the same J function, which makes it more complicated, and you need to choose out of all possible controllers the one which gets you J smallest one, right? So it's kind of tricky. So it's not exactly optimal anymore, not in general sense. All right. Okay, so let's start with that board. Okay. I need to tune all of these devices because they are not aligned correctly. Okay. It'll be fine. All right, so problem number one. Okay, first question. The system is given by a regular equation, which is dot equals ax plus bu, y equals cx, and the matrices are given like that. This is -2, 0, 1, 0. B is vector 1, 1. C is vector 0, 1. Again, this is exactly the same system as we did with Riccati equation. Same system, we want to design controller, which is u equals minus kx, regular state space controller without input, regulator. And we want to minimize J, which is integral from 0 to infinity, u squared plus y squared. So rho equals to 1. Okay. So we want to minimize that. Okay, now let's do the solution. If you remember, we need to solve now new equation. And this new equation will be a of s times a of minus s plus 1 divided by rho, b of s times b of minus s equals to 0. But for that, we first need to find transfer function, right? Because you need polynomial for a and polynomial for b. So g of s, which is open loop, it's b of s divided by a of s. So we need to find the transfer function. Okay, so what is a transfer function? First of all, we are starting with finding g of s, which will be c si minus a inverse b plus d, but d equals to 0, so okay. Okay, so far. So first we find an actual transfer function open loop for that particular system. So this will be c, which is 0, 1, times si will be ss 0, 0, minus a, which will be minus 2, 0, 1, 0, inverse times 1, 1. This will equal to 0, 1 times s minus 2, 0, 0 minus 1 is minus 1, s minus 0 is s, inverse 1, 1. Okay, so far. Minus 2. It's okay. How do you invert 2 by 2 matrix? Dividing by determinant, switching the main diagonal, putting minus minus on the not main diagonal. Okay. So it's 0, 1. 1 divided by determinant. So determinant will be s plus 2 times s minus 0 times -1, but it's still 0. Right? So this is determinant. Now here we are replacing this one with s plus 2. Here it will be 1, 0. Something like that. Yes. All right, so let's multiply. First of all, it's 1 divided by s plus 2 times. So we are multiplying from the left first. So we're taking this one times this one. So 0 times s plus 1 times 1. It will be 1. Right? I'm multiplying c by the inverse matrix. So it's 0 by s plus 1 by 1. So it's 1. 0 by 0 plus 1 times s2. So it's s plus 2. Right? And then multiply it by 1, 1. Now we actually can compute it. So it will be 1 times 1 and s plus 2 times 1. That will be s plus 3. Right? So it's s plus 3 divided by s plus 2. This is our transfer function. Okay. Now we have this part is b of s. Right anymore. This is a of s. Okay, numerator, denominator. This is all we need. So now we need to solve that actual equation like that. So let's solve that. That of equation. Remember to make the camera as well. Okay, so that equation will be our a of s is s plus 2, and b of s is s plus 3. From here, a of s will be s times s plus 2 times minus s times minus s plus 2 plus 1 divided by rho, but rho is 1. It's 1 divided by 1 if you want, times b, which is s plus 3 times minus s plus 3. So this equation fourth order. Right? Now we need to actually compute it and see what happens. So this equation will be s squared and then s squared minus 4. Remember how you do that? So kind of multiply that by minus 1, so it gets s minus 2 minus goes out, but then also that minus goes out. So you get s squared, and s minus 2 times s plus 2 will be s squared minus 4. Okay, this is algebra. Same thing here, so it will be practically minus s squared minus 9 equals to 0. All right. Now we can open parentheses, you'll get s fourth power minus 4s squared minus s squared plus 9 equals to 0. So these two come together. become 5 here. Now, can you solve that equation? Do you remember how to solve that kind of equations? Yes, you know how to solve that equation. How do you solve that equation?
Quadratic way. I mean, we can take it as x4 for x square whole square and consider it as a quadratic equation.
So this is regular quadratic equation, but in terms of s squared. You can find, first of all, root of s squared. So s squared, two roots of s squared. We'll be practically thinking about that as new variable, how we call it. It's like alpha squared minus 5 alpha plus 9, and alpha is s squared. Okay. So it's called biquadratic equation, right? It's almost like regular quadratic equation. So have the formula from that. It's minus b plus minus. Huh?
Oh, no.
Okay. So it's this one's minus this one, b squared, so it will be 25 minus 4 times 9 divided by 2. Something like that. As you can see, this is complex number. All right, so it's 25 minus 36. So this values will be 2.5 plus minus square root of 11 divided by 2g. As you can see, this is something that we got previous time. You remember the square root of 11, and you get the same kind of result. Okay, but this is not the end of it, right? You need 4 different roots, because you need to choose only the stable ones out of 4. You have 4 roots for the system 2 by 2. So S 1, 2, 3, 4 will be equal plus minus root of 2.5 plus minus square root of 11, that kind of thing. Now what? How do you find these things? It has nothing to do with controls. This is just complex numbers. How do you find root of complex number? Yeah, how to find complex root of any complex number? You can add them together, we can multiply them, divide, and find roots. How do you find roots of complex numbers? Can you find root to that particular number, positive or negative? Positive and negative will not be that difficult, but that part is more difficult. Can you do that directly on that number? Probably not. I can't. Maybe you can, I don't know. So what should I do to find square root of that thing? So what does it mean to take square root of particular complex number? So I have complex number, which is vector, practically speaking, the point here. Its coordinates alpha and beta. You put it in polar form, and then what do you do in this polar form?
Change the power.
So how do you find square root of? So polar form will look like that. You'll have some radius and angle, right? Or you can write it as r times exponent g phi. This is bullet form, right? So what do you do to r and phi when you need square root? What happens to, or any other root? I mean, it's not only square root, any root, nth root. How do you compute root of the complex number? So square root of that thing, square root of r. And what happens with phi?
You multiply by the 1 by half.
You divide by 2. The angle halves. Okay, if you want cubic root, you'll have cubic root here and divided by 3. Or by any other number, it depends on the root. Okay, so the angle gets half of it, and the radius gets actual root. The magnitude gets the actual root. Same thing here, so you need to convert this one into that shape, and then to take radius, square root of the radius, and divide the angle by 2. And you will get additional root, right? And then you have also plus minus, so you will have 2 different angles, right? And they will be reflected also, so they will be symmetrical, right? You expect them to be symmetrical because this is how you started. So technically it's important to find 2 and you know where the others should be, practically speaking, okay? So this thing, when we convert it into the right form, will be square root of 3 exponent 0.586 g, something like that. Okay, I just converted that number into polar coordinates. I'm sure your calculator can do that for you. Okay, converting into polar, then I'm taking square root of 3, dividing that angle by 2, and I get all the values that I want. Now, obviously, these values will be with different angles, so you'll have also negative part here. It's only for positive part. But you'll have also negative parts, you'll have another root like that. All right, so this will be also plus minus here. All right, so all these roots will be positive and negative roots. So the result will be plus minus square root of 3 and exponent 0.293, which is half of that number, whatever it is. All right. So S1 and 2 that we are interested in will be minus 1.658 plus minus 0.5 J. And you will have 3 and 4 with plus here. Same thing, but with plus, because they are symmetrical. I'm just converted that back into rectangular coordinates. Yeah, your calculator can do that. But you give these numbers and you get these numbers. Any questions so far? How I found the optimal location of poles? All right. So given all of that, obviously they're stable, right? These are stable roots. Stable pair of roots. So I've chosen this 2 out of 4. And now I need to design controller. How do I design controller? I can do comparison of coefficients, for example, okay? So let's say AK of S will be determinant of the psi minus A plus AK, like this thing. So this will be determinant S plus 2 plus K1. Second one minus 1 plus K1. K2. S plus K2. That can be determined. Try it more explicitly. S plus 2 plus K1 times S plus K2 minus K2 times K1 minus 1. This will be S squared plus 2 plus K1 plus K2 times S plus 3 K2. So this is our actual closed loop polynomial, characteristic polynomial. All right. So you have two coefficients that you need to compare. So this coefficient and this coefficient. Now we know where they're supposed to be. So alpha of S will be S minus S1, S minus S2. And you have them here. Okay. So I substitute, and what I get is S squared plus 3.316 S plus 3. Okay. So now this number needs to be equal to that thing, and this number should be equal to that thing. So you can clearly already see that K2 equals to 1. We have the system of equations where 3K2 equals 3, and 2 plus K1 plus K2 equals 3.316. From here, K2 equals to 1, and K1 equals, so K2 is 1. So it's like 3 here, and you cancel that with that 3, you get 0.316. And the final controller will be these two numbers. And you can compare to the solution of the Riccati equation, you got exactly the same controller. Because it is unique, you cannot get anything else. Right? This is optimal controller. How about plotting root locus? So root locus is more or less, you don't really need to plot it to solve the question, because you can do everything analytically here, as you can see. But root locus gives you an idea how it could look like for different values of rho, because we compute that for one value of rho, compute that for rho equals to 1. But now let's say rho is changing. You want to play with the rho and see where the roots could be and how symmetrical root locus could look like. Also, this is type of checking tools for your calculations to see if it makes sense, if this particular locations of poles are even possible on root locus, because root locus is particular line, right? So these values need to sit on the line somewhere. Okay. So let's see how it could look like. It's that part. Try to draw it here. This is real. Now, what are all of the poles and zeros that we have in open loop? So first of all, you start with open loop poles and zeros. So what are they? What do you have? There. So we're looking at that thing. So we have pole at 0, right? One pole at 0 or more. In open loop, we have 1. But we have also minus S. So we need to plot G of S times G of minus S. So what would be the mirror image of the pole at 0? Same. So you'll have actually double pole here. Right? What additional pole do we have? Where is the additional pole? Look there. -2. It's here. Where is the reflection of it? +2.
Yes.
Okay, how about zeros? Where is the 0? -3. So we have 0 here. It's not exactly up to scale, but doesn't matter. So where is the reflection of it? +3. So this is our initial location of things. Now, these two poles can move only two possible ways. They can move that way, or they can move that way somehow, just start moving in particular direction, because they cannot move that way or any other way. They need to be symmetrical. So they can move on J omega axis or on real axis. And this is how we choose where they actually will move, because they cannot move on J omega axis. Symmetrical root locus never moves on J omega axis. Okay, this is rule number 1 in red text, bold. Okay, remember that. Never goes through J omega axis for any row which is not infinity or 0. All right, so it can end up on the axis, or it could start on the axis, but it never moves on the axis. Right, so it cannot go that way. So they will definitely move this way. This is the only choice. So movement is here, right, between those two. And since oddity or evenness, or whatever you call it, the number of even or odd poles to the right and zeros is changing after you're jumping behind that pole, so it cannot move here. So no motion here, and then it has to move here. Right, so you'll know that it must move here, it will move there, and it will move there. But not between the 0 and pole and the 0 and pole. So they will not get to that part. So how it could look like. So these are moving that way. Okay. So this cannot move that way, so it must move that way. So they come into each other somehow, right? They have no choice. Then they meet, and then what? They have to split somehow. Okay, so one will go up, one will go down. I don't know yet which direction, but somehow. So they cannot go that way, because otherwise they would cross the J omega axis. Cannot happen. And they need to end up somehow in that 0. At least one of them needs to end up in these zeros. So they need to come somehow and get here. So probably they will go like that, some symmetric. Okay, so they will come here, one will go to 0, one will go to infinity. And same thing obviously on the second side. They will go here. Then one splits to 0, one goes to negative infinity. Something like that. Okay. And now all you need to verify if this could be on one of these plots. Right? This is what we care about. So this is 0, this is -2, and this is -1.6 plus minus 1/2. So 1.6 will be somewhere here. Probably. Okay, so the poles, the actual optimal poles will be somewhere here. This will be -0.5 and +0.5. So this is the location for the particular arc. But here you can see, for example, that if you're decreasing R, they will split even more. So they will become more imaginary. The imaginary part will grow. But if you are increasing rho or R, they will get more real. So if you want all of your poles to be real, for example, for whatever reason, you just change your rho in such a way that they will get back to that axis before they split. Okay, so you'll at least know in which direction to change your rho, or at least if it is even possible to change rho in such a way that they will become real. If you do not have any overshoot, for example, you don't want any overshoot, you don't like any overshoot, you design an elevator, you don't want overshoots, right? So you're okay with having an elevator like ours, as slow as in this building, okay? But you don't want this elevator to do something like that, okay? And then stabilize, but doing that much faster. This is the overall idea, right? When you have all kinds of design constraints, which you cannot really write mathematically. You obviously don't want elevator, which is super fast, but also making something like that, right? This is the overall idea. So here you can see how you can modify it a little bit in such a way that you will get whatever you need for your particular design. No oscillations of any kind, for example. Any questions? Okay. Now we will solve a little bit more complex problem. The system is given in canonical controller state. And transfer function is also given. The transfer function will be g of s equals s minus 1 divided by s minus 1, s plus 3. And obviously you can write the same thing as s minus 1, s squared plus 2s. Okay. Question number 1, is it detectable? Is that system detectable? How do you know what is detectable? You have some realization of the system, right? Some matrices. Detectable system means that you have, or you do not have any cancellations of them. It's obviously detectable. Or if you have cancellations, that cancellation for non-observable pole is stable. That's what detectable means. So your cancellation, which was something canceled and was non-observable, it was stable. But the cancellation might be observable right? So the pole which cancelled might be observable, and then we don't care if it is stable or unstable. So how about that system? Clearly, you have cancellation of unstable pole. But the question becomes, is the pole observable or not observable? How do you know? Without even looking at the actual realization. You don't need it. I mean, you can actually test the actual realization because I gave you canonical controller form, right? So you can actually write matrices and see if this particular +1 pole is observable or not observable, right? With all these transforms and, having a lot of manipulations, but you don't need any of it. Why is that?
It's controllable, so it's not observable.
Right. So this is canonical controller form, which by definition is controllable. So you have cancellation. So if there would not be cancellation, then we don't really know, okay? Then it's controllable and observable. Because minimal systems are controllable and observable. But in that case, you know that it's not observable. And the only pole which was cancelled is the -1. Like it's actually +1 pole, right? Unstable pole. So you know that it must be non-observable. Because the system is not minimal, you have cancellation. And the only cancellation that you have is that thing. And you know the system is also controllable. So it must be not observable because it's not minimal. Because if it would be minimal, it would be controllable and observable, but it's not. Right? So it has to be non-observable. And the only thing which is not observable here could be non-observable here is the thing which cancels. And it is unstable. So you know that the system is not detectable. Not very nice system, okay? But not detectable. This is what we know only from the definition of the question. Okay, but let's go to the actual question. You want to minimize some particular j. Integral from 0 to infinity x1 squared plus 9x2 squared plus 6x1 x2 plus rho u squared dt. Okay. So you need to draw root locus for that system as a function of rho. This is first part. Okay. Symmetrical root locus. This is part one. You see how it might look like. Any ideas how it might look like? Okay, so you have transfer function, obviously. So let's see how it might look like. Real imaginary part. So where do we have poles? So can you think about C, which is transpose multiplied by itself, will give you that matrix. So what's the C tilde? So that element by itself should be 1. Second element by itself should be 9. But cross multiplication should be 3. What are these elements? Actually easy. Round numbers. Try this one. Like 1 by 1 is 1, 3 by 3 is 9, 1 by 3 is 3. Okay? So this minimizes that transfer function if our system would be with ZC, but it's not. Is there a problem that it's not? This is the trickiest question here. Is there any problem that I will choose any C I want for my system realization? This question, which is repeating in that course multiple times. Is C affecting anything in the design of the controllers? Not at all. It's not involved in anywhere, in any formulas related to controller design, right? So I can technically pick any C to my system when I'm designing controller. This is the tricky part, to understand that you actually don't care about your C when you're designing controllers. Okay, so if you want to optimize that thing, you can optimize it for a different system, which has different zeros, for example. Okay, zeros based on that function C. Okay, but it will optimize that function now using root locus. And now use the original C with that optimal controller, because C is not changing anything in optimality at all. Right? It's not affecting anything in controller design at all. So here is the trick. What will be the transfer function if this would be your C here instead of that C? What does it change? No, it is, of course, you have different G tilde S. Now you're optimizing G tilde S instead of original G because you have different matrix C. So my claim is that optimal controller for G tilde S with ZC will be exactly the same optimal controller as to your original system, because C is not involved anywhere in computation, right? It doesn't matter if I pick any C and optimize it, right? That's how it works. So I'm saying, let me optimize that system using regular root locus, which would look like that. So it's like J tilde will be y squared plus rho u squared. So what would be the transfer function? So we still have same poles, s minus 1, s plus 3. And what will be zeros? Remember what controller realization is, controller form? What are these coefficients? Look here. These are coefficients of zeros, which means that your transfer function will be s plus 3. Very tricky choice. Now we have different kind of cancellation here. This obviously cancels with this one. And you get this thing equals to 1 divided by s minus 1. But since this is controller, it's still controllable, so I don't care. But now it becomes also detectable. That particular system is detectable. So no issues here, right? So I'm optimizing for that system now. So how root locus of that thing will look like? Again, you have cancellation at 3, which is positive 3, and negative 3. But then you have pole at positive 1 and negative 1. They still must go somehow outside. So this will go that way, crossing through, and this will go that way, crossing through. This is your root locus. Okay? And now, when we get, like why I noticed the error and mistake in previous calculation, because the optimal pole became -2, but it was not on our root locus. It cannot be. It's wrong. So previously it was moving from like -3 to left and right. It cannot be. because optimal blocking must be on the root locus, which is optimal one. Okay. All right. So now we have that second part. And second part goes that we have only 1 divided by s minus 1 left, right? So the gs, remember, tilde s is 1 divided by s minus 1. So a is s minus 1 and b is 1. This is where you get this thing. Okay, equals to 0. And then you get one optimal pole at -2. Now, obviously, you need to keep the additional pole because system of second order will have another pole. And this pole will be the cancelled pole s plus 3. Right? So now we do a regular design, alpha of s. Desired will be s plus 3 times s plus 2. These are two desired poles. And again, you cannot move that thing because cancelled. You keep it as is, and it will be positive and stable, obviously. And this one is of yes. Question? Yes.
A of S is the numerator or the
I'm sorry?
A of S?
A of s, yes.
It's the numerator or the denominator?
It's denominator.
Denominator.
A of s is denominator, which is that one.
Yeah. So when you use the S or L over why A of S is S minus 1?
Because it's s minus 1. This is the denominator. Numerator b is 1, and a is s minus 1. Or you can take all of them. I mean, technically, you can take both of them, okay? Let me just move the camera. We can do different, okay? Let's make it full calculation, okay? So g tilde of s is s plus 3 divided by s plus minus 1 s plus 3, right? So a of s will be s minus 1 times s plus 3. And a of minus s will be minus s minus 1 minus s plus 3, right? Plus 1 divided by rho, which is 3, times b, which will be s plus 3. B of minus s will be minus s plus 3, and it all equals to 0. Right, so this is a full equation, full order equation. But look at these things. So they appear in both things, so they cancel out, right? Because you can divide by both of them, both sides. Same thing with that thing, right? This thing cancels out. So you can divide by s plus 3. Right, so what is left? That thing. Okay? So even if you write that entire complete thing, it will still cancel out algebraically completely. So you will get that equation and will have only one of the roots. But second root will be that thing, like s equals minus 3, right? It's still in that equation. It still solves that equation, s equals minus 3, right? It just cancels automatically. All right, so we have the desired polynomial, we have ak of s equals determinant si minus a plus bk. And this will be whatever determinant, comparing coefficients, and finding solution of k optimal, right? Any questions on that? All right. If you don't have any questions, that's it for today. Thank you.